Good morning. We have been discussing a situation where we have two slits and we have a source which sends out electrons. These electrons are incident on the two slits. We had labeled the slits 1 and 2. The electrons which pass through the slits are incident on a screen and we have a detector which can be moved to different points on the screen. And what we find when if we do this experiment where electrons are shot here from the source over here. So, you have an electron gun which shoots out electrons and you have a detector here on the screen which can count the electrons arriving at any particular point. So, what happens when you do this experiment is that the detector will detect electrons. So, it will always find that either there are no electrons incident or there will be a single electron. So, you never receive half an electron, you always receive either a full electron coming or no electron at all. So, the detector, if you switch on the whole experiment, keep on shooting electrons and you put the detector here for a time period, let us say 5 minutes and wait, you will find that there will be certain counts recorded by the certain number of electrons recorded by the detector. This is going to be an integer because you will always find that there is going to be either one electron coming or nothing at all. So, you will get some count, maybe 0, 1, 2, 3, 100, 1000 something. And then you can repeat the experiment placing the detector at different positions and then if you know the number of electrons that are shot out in that 5-minute duration, then you can divide the counts that you receive here by the total number of electrons that were shot out in the same time interval, and by dividing these two we get the probability of an electron coming at any point on the screen. And if you do this experiment, you will find that the probability distribution looks something like this. It will have a peak and then there will be a pattern of maximas, minimas, okay, let me draw this again for you. This is picture has not come out well. So, if you plot the probability as a function of position on the screen, you will get something which looks like this. So, you will get this is the probability of finding the electron on some point in the screen. This is the center of the screen and you will find that you will get a probability pattern which looks just like the interference pattern which you expect to get when we had discussed the Young's double slit experiment. I also told you that the only way you can explain this probability distribution on the screen is by associating a wave psi with every electron. So, this wave psi is associated with every electron, and this wave I am referring to as the probability amplitude. It is a complex number which is defined everywhere. So, let us just imagine one electron. So, every electron has a wave associated with it. So, when we have when the wave associated with one electron. So, let me draw the wave front. This is the wave front, one of the wave fronts of the wave associated with one electron. Let us take a possible situation where this looks like this. I have also told you that this omega is related to the energy of the electron, which is h cross omega, and this k is related to the momentum of the electron, h cross k. So, let us just visualize this wave. This wave is a plane wave, and associated with the electron, with an electron with energy E and momentum p, where E is h cross omega, p is along the x axis is h cross k, associated with an electron with this energy and this momentum, we write down a wave which looks like this. So, this wave, the wave front corresponding to this wave, is propagating forward. That is a forward propagating wave which I have written down here. Now, this wave is incident on these two slits. Now, recollect what happens when a wave is incident on two slits. Each slit now acts like a source for a secondary wave. So, you can think of each the secondary wave coming out from here, and if I wish to calculate the resultant wave psi at this point, it will have two contributions. One contribution will come from the first slit, the second contribution will come from the second slit. So, the way we can explain this kind of a probability distribution is by associating a wave with every electron, and the wave corresponding to an electron when it is incident on the two slits, each of the slit now acts like a source for a secondary wave. If I wish to calculate the wave psi at this point, the probability amplitude psi at this point on the screen, I have to add up the contribution from this secondary source, and this contribution we called psi 1. We have to also add to the contribution from this secondary source psi 2, slit 2, which is psi 2, and the resultant at this point is going to be psi is equal to psi 1 plus psi 2. And to find the probability of the electron arriving at this point, we have to add up, the probability is calculated from the probability amplitude by taking its mod and then squaring it. So, it is just like the way you calculate the intensity of an electromagnetic wave or a sound wave. You take the modulus and square it of the, so take the amplitude, find its modulus and square it, that will give you the intensity for an electromagnetic wave or sound wave. For this probability amplitude, you take the modulus and square it, it gives you the probability of finding the electron at that particular point on the screen. So, if you calculate the psi, the probability amplitude at that point on the screen, and then take its modulus and square it, it gives you the probability of finding the electron at that point. So, let me make the key point once more. If you think of the electron as a particle, you would associate a trajectory with the electron And if I were to tell you that the electron left here and was detected at this point, classically you would think of there being two possibilities, either one trajectory going through this slit and then coming here. There would also be another possibility where you had a trajectory where the electron went through this slit and arrived at over here. So, there are two possibilities by which the electron can arrive from somewhere on that side to these two, to this point. It could be either through this slit or through this slit. Now, if you adopt this picture, then the probability of the electron arriving here would be the probability that the electron came through this plus the probability that the electron came through this, and these, the probability being a positive number, would always add up. So, the resultant probability of the electron coming here would be the sum of the probability that it came through this or it came through this. And one could determine the probability of the electron coming to a point through this by closing this and opening this. One could determine the probability of the electron coming here through this by closing this and opening this, and then you would add up the probabilities to calculate the probability of the electron coming here when both are open. But if you do the experiment, you find that this is not true. Instead of the probability increasing when I open both the slits, and there are places where the probability goes down. So, the way around this, as we have discussed, is to introduce a wave associated with the electron, and this wave is what we refer to as the probability amplitude. So, now when there are two possibilities, the electron can go either through this or through this. You have to add up the probability amplitude contribution for this possibility where the electron goes through slit 1 with the probability amplitude contribution from slit 2. So, you have to add up the waves, that contribution to the wave at this point or contribution to the probability amplitude of the electron at this point. To calculate this, you have to add up the contribution from possibility where the electron goes through slit 1, which is psi 1. You have to this you have to add up the contribution from the possibility that the electron goes through slit 2, which is psi 2. So, both of these, the probability and amplitude contributions from both of these have to be added to determine the total probability amplitude at this point, and the square of the probability amplitude gives you the probability of the electron coming here. And since this probability amplitude at that point on the screen, at this point of the screen, is the sum of these two probability amplitudes, when I take the modulus and square it, this is going to be equal to psi 1 plus psi 2 square, and these probability amplitudes are necessarily complex quantities. So, when you calculate the probability of the electron arriving at any point when both slits are open, it is going to be the probability when one slit is open plus the probability that the next slit is open plus 2 times the square root of P1 P2 cos delta, where delta is the phase difference between these two probability amplitudes. So, it is the phase difference between this contribution from this possibility plus the contribution from this possibility. So, you see, the main thing is that the probabilities of do not add up. So, when you have two alternatives that the electron can take to reach this particular point on the screen, this particular point, then you do not have to, you cannot add up the probabilities to get the resultant probability of the electron arriving there. You have to add up the probability amplitudes, and the probability amplitudes are necessarily complex, and you have the phenomena of interference, because the probability amplitudes can be in phase, they can be out of phase. If the probability amplitude contributions from the two possibilities are in phase, the probability increases. If you are at such a position where the probability amplitude contributions are out of phase, the probability actually goes down, it goes below the probability when only one slit is open or only the slit 2 is open. So, you have the phenomena of interference. Now, let us ask the question first question that we can ask is, what happens to our old picture where the electron arrives at this point either through this or through this? The moment you think of the electron as a wave, you see you cannot think now, you can no longer think of the electron as a particle, because a particle has a well defined trajectory. We now have to abandon that picture when we want to understand this kind of a situation, and we have to now think of the electron as a wave. So, we have a single electron, the wave corresponding to that single electron is there everywhere. If you write down a wave which looks like this, this is defined all over space. So, the electron which is let out from here is represented by a wave. The wave is defined all over this. The wave front is propagating forward. When this is incident on the two slits, some of the wave passes through this and reaches here, some of the wave passes through this and reaches here. So, now you see that the wave which is distributed all over space can simultaneously pass through both the slits and arrive at the detector, and you have a value which you get by superposing these two contributions over here. So, you have to abandon the picture that the electron goes either through slit 1 or through slit 2. The wave actually goes through both and arrives at this point. And the resultant at this point is the superposition of both of these contributions. These two contributions may be in phase or out of phase, and they may add up or cancel out, giving rise to this kind of an interference pattern in the probability. So, the electron is not going, you have to abandon the picture where the electron goes either through this or through this. The wave corresponding to the electron goes through both. So, it is as if the electron were actually going through both, and you have to calculate the probability amplitude over here by superposing these two contributions. So, it is the electron is actually distributed all over this space. The wave corresponding to the electron is distributed all over the space, and in some places the two contributions, it is at any point here it is a contribution of sum of two contributions. At some places the two contributions add up, and some places they subtract. Now, so we have this electron distributed all over this region, the wave corresponding to the electron at least is distributed all over the space. Now, when you put a detector and detect the electron, you do not detect a fraction of the electron, because which you may think is what you would expect, because the electron, as I have told you, is distributed all over this region. So, you would expect, you may think that if I were to put a detector here, I would detect the part of the electron that is here. No, this probability amplitude, the wave corresponding to the electron, it tells you the probability of finding the electron somewhere. When you actually detect the electron somewhere, you will always get a full electron. So, the electron, the moment you make a detection, the electron gets localized to that particular point. Until you make the detection, you cannot say where the electron is. The wave corresponding to the electron is there all over. The moment your detector gives you a click which tells you that the electron is here, the electron, you know now, is at that instant when the electron is detected, you know that the electron is here and nowhere else. So, this is the kind of picture we have to adopt if we wish to explain, if we wish to understand this kind of probability distribution that is observed on the screen. And here we have to allow for the possibility that the electron passes through both, the wave corresponding to the electron passes through both the slits. Or another way of putting it is that we cannot answer the question through which slit the electron actually passes. The wave corresponding to the electron passes through both the slits. So, you may say that the electron passes through both the slits and arrives at the detector. you have to really abandon this picture where the electron either passes through this or through this. Now, one could modify this experiment slightly. So, let me now discuss that. So, what one could do is one could put a light source somewhere over here. So, suppose I were to put a strong light source somewhere midway between the two slits, such that this light source illuminates both the slits. Now, if an electron, let me draw this picture again. So, we have the two slits, and we have the source which shoots out electrons, and we have a strong light source over here. We have the screen over here. We have the strong light source which illuminates both the screens quite strongly. So, now if I have an electron which goes through slit 1 and then arrives at the screen, the moment the electron appears at screen 1, it will scatter some of the light which is being sent from this light source. We have learnt about this scattering. So, the moment the electron is incident, so the electrons are being shot out from here. If the electron passes through slit 1, it will scatter some of the light incident on slit 1, and you will see that there will be a sudden scintillation. It will suddenly get brightened over here, because the scattered light you will be able to make out the scattered light, and then you may find a click at some point at a detector at some position. So, you will now know that for sure the electron has gone through slit 1 and arrived over here. If you wait for some more time, then you will find that there is a sudden brightening over here. The electron has scattered a photon over here, and then you will record a click at some detector on the screen, and you will know that the electron has come through slit 2 and then arrived at the screen. So, by such an experiment you will be able to make out through which slit the electron has gone and hit the screen over here. So, by such means you can now determine through which slit the electron is going. So, now we have a situation where you can tell through which slit the electron goes and then hits the detector. You are no longer in the situation which you had earlier, where you could not tell through which slit the electron goes. And it so happens that the moment you put a light source here which can detect the two electrons, whether the electron goes through this slit or through this slit, it so happens that the interference pattern which you had earlier when you were not able to tell through which slit the electron went is now washed away. What you now get will look like the sum of the two probability distributions. So, it will have one peak somewhere here, and then there will be one more peak somewhere here. It will look like this. It is the sum of the two probability distributions, one of the electron going through this slit and then arriving at the screen, the second being of the probability of the electron going through this slit and arriving on the screen. Now, you see why does this happen? We can also understand that the moment you see the light emitted by this source, we have already learned that the light you should think of the light in terms of photons, and the photons carry energy and momentum. So, when an electron scatters a photon, there will be an exchange in the electron's energy, change in the electron's energy and momentum. So, the wave which was coming the wave associated with the electron is now going to get disturbed, and the fact that you have disturbed the electron will wipe out the interference pattern that you would expect if you were not to disturb the electron. So, the disturbance, the momentum imparted to the electron will give it a kick, and that you cannot predict where the electron is going to go as a consequence of that kick. So, and this disturbance also wipes out the interference pattern, which you would have seen if you were not to put in this disturbance. So, the act of determining through which slit the electron passes disturbs the wave associated with the electron, and this interference pattern, the interference pattern is washed away, and this is what you get. Now, you could try to overcome this restriction. So, one possible thing that you could possibly think of doing, a possibility which you may consider, you might consider to try and overcome this, so that you could detect both. Suppose you wish to try and detect both, that is both the interference pattern as well as determine through which hole the electron goes. This would be something which would contradict everything, right. The interference pattern we see arises because of the possibility that the wave corresponding to the electron can go through both of these. But if you knew through which hole the electron slit the electron went, then there would be no need for considering the wave going through both, and if you were to still detect the interference pattern, then we know that there would be some kind of a contradiction and we would be in deep trouble. So, the question is, does this thing arise, or is there some means by which it never arises? Okay. So, you may try to make such a situation arise by reducing the intensity of the light. Now, what will happen if you reduce the intensity of the light is as follows. If you reduce the intensity of light, you will find that there are some photons, there are some electrons which do not scatter a photon over here, but reach the detector, reach the screen, because you will find that there will be clicks on detectors located at the screen, but there will be no corresponding brightening suddenly at near one of these two slits. So, you will not know through which of the two slits the electron has gone, but you will find that the electron has reached here. This will sometimes you will find that the electron produces a sudden brightening near slit 1, sometimes it produces a slight sudden brightening near slit 2, followed by a click on the detector on the screen. So, when you reduce the intensity of the light, you do not reduce the energy or the momentum of the photons. What you do is you reduce the number of photons, and if you reduce the number of photons, then there will be some electrons which will get through the slits without being able to scatter a photon, and such electrons will not produce any kind of brightening either here or here, they will just directly reach the screen. Some other electrons will scatter photons, and for those electrons you will know that it has gone through either this or through this. Now, in such a situation, if you record the electrons which produce scattering here, so these are the electrons which you can tell that this electron went through slit 1, this electron went through slit 2, this electron went through slit 2, that went through slit 1. So, for these electrons you will find that the probability distribution looks just like the same good old thing that you would expect if you did the experiment with bullets. The probability distribution would be the sum of the two probabilities, one of the electron going through this, the other for the electron going through this. Whereas, for the electrons for which there was no scattering, you will get, if you plot the probability of those electrons arriving on the screen, for those electrons you will get the interference pattern which you would have got if this light source were not there. So, you see, for the electrons for which you can tell through which slit it has gone, the interference pattern is washed away. For the electrons for which you cannot tell through which slit it goes, the interference pattern remains intact. Now, you could try another thing. You could try to reduce the wavelength of the light that is coming out of this source. When we discussed Compton effect, we learned that the energy and the momentum of the photon are proportional to the frequency or inversely proportional to the wavelength of the light. So, if you use light of a very large wavelength, you may be able to detect scatter the electron. So, you will be able to detect the scattered photon. So, if you get scattered photon from here, then you will know that the electron has gone through this. If you get scattered photons from here, you will know that the electron has gone through this. So, if you can reduce the wavelength, so make it so small that its momentum, the momentum of the photon is very small. So, you can then scatter the electron without disturbing the electron too much, and maybe you will still get the interference pattern. So, let me make the point again. You can try modifying this experiment by reducing the frequency or increasing the wavelength of the photon, with the hope that it now carries a very small momentum. The photon now carries a very small momentum. So, even if it scatters of the electron, it will not disturb the electron too much, and I will still see the interference pattern because the disturbance is not too much, but the photon would have got scattered and I will be able to say through which slit the electron has gone. But unfortunately, in this situation, what will happen is as follows. We have learnt that the resolution of any optical instrument, anything that depends on waves, is the resolving power to resolve. The angular resolution is proportional to the wavelength. That is, the larger the wavelength, the poorer the resolution, in the sense that I will not be able to resolve very fine angles, I will only be able to resolve very large angles. So, if you increase the wavelength and do this experiment, it so happens that if you choose a wavelength which is sufficiently large, that the momentum transferred to the electron is not is sufficiently low, so that the wave is not disturbed and you do get the interference pattern. It so happens that in all such situations, the resolution is so poor that you are not able to say through which slit the electron passed. Let me make this point again. If you increase the wavelength, if you make your wavelength very large, it is true that the momentum transferred to the electron is going to be small. You will still get the interference pattern after scattering, but you will not be able to say, the wavelength being so large, you will not be able to say whether the electron passed through this or this. The resolution is going to be larger than this, and it is going to be, you are going to get a very coarse picture. So, you will know that the electron has passed because you will see the scattering pass through one of these, but you will not be able to tell through which one it has passed. So, you will see the interference pattern, but you will not know through which slit the electron has gone. So, there is an underlying principle which is on which the whole of quantum mechanics is based. The underlying principle is the Heisenberg's which was originally proposed by the German scientist Heisenberg, uncertainty principle. Heisenberg's uncertainty principle. So, In most general terms, the Heisenberg's uncertainty principle states that if there are two different alternatives which the electron or the particle could take, for example, in the situation which we have been considering, the two alternatives are the electron could go through this slit or this slit. Then what the Heisenberg's uncertainty principle states is that if the act of measurement, if we try to measure through which of these two alternatives the particle chooses, if we try to measure in this particular case through which of the slits the electron goes, then the act of measurement will disturb the electron so much. If we can determine through which of these two slits it goes, or if more generally if there are two alternatives, if we actually determine through which of these two alternatives it chooses, then the act of measurement will disturb the particle, in this case the electron, so much that the interference will be wiped away. And if the interference is wiped away, then you have to just add up the probabilities for the two alternatives. So, in such a situation, the probabilities P12 is going to be P1 plus P2. So, if you measure the act of measurement itself is going to disturb the system so much that you will not be able to, you will wipe out the interference pattern. So, if you make a measurement which can tell you if there are two alternatives for the system, and if you do not know which of these two alternatives the system is going to go through, then you have to add up the probability amplitudes and you will get an interference. Whereas, if you make a measurement and determine which of these two alternatives the particle chooses, the act of making the measurement is going to disturb the system so much that the act of measurement itself, that this disturbance introduced by the act of measurement is going to wipe out the interference pattern. So, let me repeat again what the summary, the gist of what we have been, what I am trying to get across, and what I am trying to get across is a different picture which has to be invoked when we are dealing with the microscopic world, with things happening in the microscopic world. You may ask the question, why don't we see this kind of an interference pattern in the probability distribution or in the distribution of bullets, for example, in the distribution of bullets. So, if I shoot two bullets, that is the experiment, that is the situation which we have discussed in the last lecture. If we shoot bullets onto two slits and observe the probability distribution of the bullets on a screen placed behind the two holes or the two slits, then the probability distribution when both slits are open is the sum of the probability distribution when only one is open, that is only when slit 1 is open, which is what is shown in red, and only when slit 2 is open, what is shown in green. If I open both of them, I will get the sum of both of these probabilities, which is what is shown in black. The question is, why do we not see the interference pattern corresponding to the bullets? So, let me remind you that the wavelength corresponding to this probability amplitude wave, remember that this probability amplitude wave is the same thing that which we have been talking about today and in the last lecture, is the same thing that de Broglie had hypothesized. So what we have been discussing is basically the interpretation of the wave originally hypothesized by de Broglie. And remember that the wavelength is expected to be h by the momentum p. And the value of h 6.6 10 to the power minus 34 joules second. I am not writing the units, we are working in SI units. And let us also estimate the typical momentum of a bullet. So, of some classical particle, need not be a bullet. So, let us take the mass to be say 10 grams, some number which I am just putting in. A bullet need not be really 10 grams, but this is just to get an idea. And let us take a speed of of let us say 1 kilometer or 100 meters per second. So, 100 meters per second. So, 10 grams 100 meters per second. So, 10 grams would be 10 to the power minus 2 kg, and if I multiply it with 100 meters per second, so I will get a factor of 1 in the denominator, and the wavelength, this is joule second. Okay, let me put the units. So, the wavelength is going to come out to be of the order of 6.6 into 10 to the power, this is minus 2, this is 10 to the power 2. So, this exactly cancels out in the denominator, and this is of the order of 10 to the power minus 34 meters. And so, the wavelength of, if I were to associate a wave with the bullet, the wavelength would be of the order of 10 to the power minus 34 meters. And remember the Young's double slit experiment, the interference pattern in terms of angle, if the in terms of angle subtended over here, in terms of that, the spacing between the maximas is of the order of lambda by d, where lambda is the wavelength of the wave, d is this separation. So, if I take the separation to be something like 1 micrometer, so 1 micrometer lambda by d, so this is the value of lambda, and the spacing between the two slits let me take to be 1 micrometer. So, lambda by d is going to be of the order of 6 into 10 to the power minus 28 meters, right. I am dividing 6.6 10 to the power minus 34 divided by 10 to the power minus 6. So, I get 10 to the power minus 28 meters. So, this is now this is lambda by d, it is an angle in radians. And if I put the screen 1 meter away, then I am going to get, this is going to be the spacing between the maximas. If my screen is 1 kilometer away, then this is going to get multiplied by 1000, and still it is a very small number. So, the intensity pattern that I am going to see on the screen over here, if the screen is 1 kilometer away from the two slits, there are going to be these intensity variations, but the spacing between the maximas is going to be extremely small. For 1 kilometer, it is going to be 10 to the power minus 25 meters, because this is the angle multiplied by the distance, I will get the separation between the fringes. So, this spacing is going to be of the order of 10 to the power minus 25 meters, but it is going to be very close. So, finally, what we are going to get is a set of maximas which are very close to each other, the spacing being 10 to the power minus 25 meters, and these maximas are going to be so closely spaced that what we are going to see, actually what we are going to be able to make out is going to be the average of this, which is going to look something like this. The probability distribution, which is going to be the sum of the probability distribution when corresponding to the two slits. So, the point is that the interference pattern varies, the distance between the maxima is so small that you cannot make it out, and what you see looks like the classical expectation. Which is why you do not see this for macroscopic objects. So, let me now again come back to the point which I was making. So, in the situation where we have, let me recapitulate the key points which I am trying to make. So, in the situation where we have an electron, for example, going through these two slits, or where there are various alternatives that the electron can take, or where any microscopic particle can take, if there are various alternatives. So, here there are two alternatives by which the electron can reach here. It can either go through this slit or it can go through this slit. Then we have to add up the probability amplitude corresponding to each of these alternatives. So, if there were three alternatives the electron could have taken to arrive at the screen, then we would have had to add up the contribution from the probability amplitude for three such alternatives. So, if there was three slits, then I would have had to add up the probability amplitude contribution from three such slits, and there would be psi 1 plus psi 2 plus psi 3. And these probability amplitudes are necessarily complex quantities. These are waves defined all over. Now, when we want to calculate when we actually do a measurement, and the quantity which you can predict for the measurement is only the probability. You cannot calculate trajectories for electrons and such microscopic particles. You have to think of them in terms of waves, the probability amplitude wave. Now, when you actually go and put a detector and make a measurement, although the wave is distributed all over space, you will always find that the electron is there at only one point. And what you can predict is the probability of finding that electron at different points. And that probability is to be calculated by taking the modulus square of the probability amplitude. This gives the probability. And the third thing is that if we do a measurement which can tell us through which of the alternatives is being chosen by the particle. So, in this case, if we do a measurement which can tell us through which of these two slits the electron is actually going, then the interference is washed out and the resultant is just the sum of the probabilities that the electron goes through this or the electron goes through this, or it is just the sum of the probabilities that the particle chooses either alternative 1 or alternative 2. So, that is the third thing. If you make a measurement, then this is going to be P12. When you do not make a measurement, the act of measurement disturbs the wave, and as a consequence the probability is now the sum of the probabilities corresponding to the two alternatives. So, these are the three main points which I have been trying to make. We have to abandon the particle picture over here. If you wish to understand and model the propagation of the electron through these two slits, it has to be thought of in terms of waves. We have to abandon the particle picture where the electron has a definite position and momentum. You know for sure where, you know for sure through which slit the electron goes. This has all to be abandoned. We have to think of this whole thing where of the electron incident on these slits. We have to think of it in terms of a wave incident on the two slits. This wave splits into two, it goes through both the slits and then arrives at the detector. Now, a final point which I should make before I close. We have been discussing a situation where there is only one electron, and so a single electron's wave goes through both, and the single electron is detected at one point on the screen. So, every time an electron goes through this, you will get one click over here. From just sending one electron, you will never be able to get, you will not get this full probability distribution. The same experiment has to be repeated many times. So, you have to actually send many electrons through this. When you send many electrons, you will get a variation in number count. So, if you put your detector here and send many electrons, you will get a certain number of counts, which you can convert to a probability. Put your detector slightly different position, again send many electrons, count how many of them arrive here, and then that will tell you the probability of the electron reaching here. The experiment has to be repeated many times with many electrons to finally get this full probability distribution. One electron will only give you one count at one position. From there, you will not be able to tell the probability distribution. It has to be repeated many times. Finally, I should also tell you that you do not have to necessarily consider a situation where you are sending the electrons one by one, but the point that you have to remember is that the waves corresponding to two different electrons do not interfere. It is the interference occurs only between the wave, only for the wave of a particular electron. It interferes only with itself. It does not interfere with the wave corresponding to a different electron. It is as if these two waves are incoherent. So, if you have many electrons being sent out, we do not have to bother about the possibility of one electron's wave interfering with the other electron's wave. That need not be considered. It is only the wave of a single electron which passes through both of these and then produces the interference pattern over here. We can never simultaneously record the entire interference pattern. What we can do is we can record the electron at a single position, and by repeating this many times, we can construct the full probability distribution, which is the mod square equivalent of the intensity pattern that you get for light or sound. Here it is the probability distribution. We can get that by sending electrons one after the other, or by sending many electrons and looking at their distribution. So, this brings to a close today's lecture. In the consecutive lectures, the forthcoming lectures, we are going to develop on the mechanics, on the way to manipulate this probability amplitude, which we are also going to refer to as the wave function, and that takes us into the realm of wave mechanics or quantum mechanics.